Okay, we're in the last 2 weeks of class. And we're going to talk about power functions and end behavior. And then we're going to talk about polynomials. Did anybody have any big questions after doing the prep assignment? Anybody?
The 5.1. Isn't what we did
Yeah. 5.1 was basically talking about limits at infinity and limits going to infinities. And I encourage you to watch Friday's video for that discussion more on limits. And then now what we're going to do today is go from the power function to the polynomial. From the power to the polynomial today. And it's all in this packet here. That I put to be due. This was supposed to be due today. Let's see, how many people did it? 5! Beautiful! And I think that it wasn't due till after. Yeah, right? It's like midnight tonight. Okay, anyway. So I put this power and polynomial notes, which is a thing that I like. I feel like the thing that I like about this is that it provides more of the pictures for you. And that our textbook has, our textbook asks you to generate a lot of the images, which is good, but I feel like for time, it's better just do my handout, okay? Just do my handout. Now, who was not here on Friday to receive a printed copy? Russell? Sophia? Were you here Friday? Oh, there was no class on Friday. I'm talking about Wednesday. Did you get this? Yeah. You got that? Okay. Helen, I don't think you were here on Wednesday. You have this piece of paper? This is stack of papers? Okay. This is what we're going to do. Now, in the textbook, they have some really great, they have some really great explorations. I'm not going to do that for 5.1. I'm just going to have us do this, and I just want to remind you that if you go to Desmos, you can mess around with these functions very easily. So if I just do y equals x to the p, okay, I'm going to add a slider for p. And as I increase p, weird stuff happens. Okay, if p is like some odd number, if p is a decimal, it looks weird, right? But if p is like an odd number like 5, remember we get an x to the 5th power, we have odd symmetry. If p is an even number like 4, we get an even symmetry, okay? And there's an important point we want to look at, which is as the power increases, look at the behavior between 0 and 1. So if I have x to the 0 power, that's just a horizontal line, right? Okay, so everybody look what happens as p increases on the interval from 0 to 1. Does anybody know what's going to happen? Does anybody know what's going to happen? Will it stay the same? This particular point will stay the same. And that makes sense because 1 to the power of whatever is just going to be 1. 1 to the power of yo mama is just going to be 1. So if I press play, now lots of weird stuff happens on the left-hand side, but look what happens on the right-hand side. Okay, now we're going back to 0, boom. Now we're increasing p, increasing p, increasing p. Okay, now we're going back to 0, boom. So what would you say happens as we increase the power? What? Say the words you were saying, go ahead. Which slope?
From 0 to 1.
Now the slope from 0 to 1 always stays the same because the function passes through 0, 0, and 1, 1, no matter what p is, right? But as I increase p, there is an increasing slope. It's weird, but let's be more precise. The slope right here near 1 increases, right? Gets like sharper, gets steeper right there. But the slopes near 0 get smaller. Whoa. So one of the things we can do is we can say that for something less than, by the way, something less than, oh, come on in, hi. Something less than, something less than 1. We get like something that curves up like that, like the square root, or in this case, that's actually a 5th root, right? But as I increase this, right, so here when p is 1, I just have the straight line. When p is greater than 1, I start to curve down to concave up, right? And then as I increase it, this corner kind of gets sharper, right? Okay, so now let's do the guessing game. You are assigning these function values to these curves, okay? And I would like you to do that now. Which one is x squared? Which one is x cubed? Which one is x to the 4th? And which one is x to the 5th? Are we ready? Go. Discuss. Do it. If you haven't done it yet, do it now. If you have done it, turn to somebody and say, this is what I did. This is what I got. Power and okay. Someone tell me what they did, what they thought. Where does x squared go? What do you think, Helen? Did you do it yet? Just do it now.
The darker one on the thing.
Okay, so Helen says this is the darker one. Do we agree with that?
Yeah.
Why is that? Also, we know it's even. But why isn't the light gray one a parabola? So we know that x to the squared and x to the fourth have to go here. But we know this one, y equals x squared, is going to be a little more chill. Doesn't curve as sharply as the higher power, right? So those are the right answers. Good job, Helen. I didn't let you explain, but someone else. Talk about this one. Which one's which? Anybody? Yeah. Great. Now, what do you think happens when we make them negative? Now they get asymptotes. But first of all, look at these two curves. Which one, what kind of symmetry does this have? It has blank symmetry, which is like a mirror image on the y-axis. What do we call that? What'd you say? Blank symmetry. Blank symmetry. Okay? So to remind you, even symmetry means that it's like mirror image around the y-axis. Odd symmetry means like if I go right through the origin, I get to another place right there. That's odd symmetry. So I just told you the answer. This is even. This is even symmetry, and this is odd symmetry, which means this must get to the x to the -2, x to the -4, and this must get the x to the -3, and x to the -5. Okay? So which ones go where? Oh,
The dark one.
the dark one is what?
The dark one is x to the power.
Ah, and therefore this one is y is equal to x to the power -4. Which, my friends, by the way, is, if you remember, this is 1 over x squared. That's the same thing. This is 1 over x to the 4th. Same thing. Right? So you kind of get this idea that the higher power makes it move faster. It's like sharper, right? So then, which one is the darker one over here? Y equals x to the -3, that's what I think. And then this is y equals x to the -5. Okay? And if you're not sure, just plug them into Desmos and see. Like, literally try them. Now I can make these negative, okay? Let's see, when it's negative even power, you just look at the left-hand side. Now it's going to decrease. Power's going down. Power's going up. Power's going down. Okay. Oh. And we see it going odd, even, odd, even, odd, even, odd, even, flashing up and down. Odd, even, odd, even, odd, even, odd, even, odd, even, odd, even. When it's up, it's even. When it's down, it's odd. On the left-hand side. Boom. Cool, man. So that's how it works. The sharper it is, the higher the power. And that sharpness has to do with being greater than 1 or less than 1. What happens when you raise something like that to a power. Now, we could talk about that more, or let's move on. Ready? What about this one? Fractional powers. Which one is a square root? Which one is a cube root? What do you think? Yes. The what?
Oh, wait, no.
Yeah. I agree with you. Right? It's more chill, the darker one. The light gray one is a little sharper. That's called x to the 1/3 power, which is the same thing as the cube root of x. Okay? So these are the basic power function shapes. Okay? And I wanted to just make sure, hey, wow. Hey, I saw you in Redwood City. You were at Safeway.
I don't go to Safeway.
Yeah, but your face was on a milk carton. It was like missing person. That joke doesn't fly anymore because they don't put missing persons ads on milk cartons anymore, do
But
they?
I get it.
They used to do that.
Yeah.
Like seriously, like you'd be like missing person ad on the milk carton. I know they haven't done that for like a decade, but it's true. I was just teasing. Ready? So. Oh, stylus. Okay. So anyway, here's the part that's not in the textbook, which is kind of why, but I feel like it's really important, but it's not in the textbook, which is this next part right here is if you go to the other side. We're not going to do example. I'm going to skip example 1. I mean, I can show you how, but the main thing I want to do is this definition of variation, proportionality, or inversely proportional. Okay, so I will put this in my notes and also I'll show you, but first I want to do this because this is more important. How many of you had a physics class? Yeah? Well, what's that? Oh man, we lost Helen. Helen, do you already do all this? Back page. Okay. Quantity y is called directly proportional to a power of x if, okay, directly proportional. If y is equal to k times x to the n, like that. That's multiplication. Basically, if I say directly proportional, it means that we're multiplying by some constant times the power of n, okay? Directly proportional means that this quantity right here is equal to some constant times the power of n. Examples include, I have inverse proportion in my mind. Oh yeah, the force, like from physics, the force that a spring pushes is directly proportional to how, or the force that a spring pulls on you is directly proportional to how far you stretch it, right? So you know if like you stretch a spring, it gets harder. The distance you pull it is it's like a multiple of how it's the distance you pull it times some constant is how hard you have to pull. That's called direct variation of the first power of x, okay? Constant y is called inversely proportional to a power of x if y is equal to, what do you think it is? Yes, reciprocal! But in this case, it's not inverse function, it's inverse proportionality. It means you're dividing by the, okay? So inversely proportional means we have some constant and we're dividing by it, right? So you're like dividing by the power of n, okay? So the pressure P of a gas is inversely proportional to its volume. So my friends, literally all you're doing is just saying P is equal to K over V, which is actually true. It's called the ideal gas law. PV equals nRT, physics. But the thing I want you to know is that you could translate this phrase of is inversely proportional to as like P is equal to some constant K divided by V. We need information to find exactly what that K value is. We don't know what K is just from that, but we know that the function looks like that. And K is known as the constant of proportionality. Did you already know this? Did you know this already? Are we learning something new today? Maybe a little. Great! The work done W. Hey! I just said this. The work done W in stretching a spring is directly proportional to the square of its distance, D. Directly proportional to the square of the distance. Because force times distance is work. Anyway, I was saying slightly different formula verbally. But let's translate this one. How do we translate it? Directly proportional to means K times the square of the distance D. Okay, so here I'm gonna do like directly proportional to, that's K times square of the distance D is literally just D squared. And we would say the work is, where K, so here I'm translating the term directly proportional to. Work in stretching a spring is W equals, right? And here's the square of the distance. There. Remember? So how does that sound? Make sense? Okay. The distance D of an object away from a planet is inversely proportional. D is equal to inversely proportional to the square root of the gravitational force. Whoa. Inversely proportional to. Inversely proportional to. What does it say? Inversely proportional to means K divided by the square root. Raíz cuadrada. Not cuadrada, raíz de cuadrada. Square root means to the 1/2 power, which is the same thing as that, okay? So this is f to the 1/2, which is also equal to K over the square root of f. So that's how we translate these things, is my point. Power functions arise from, like, a lot from physics. These are all physics examples. They don't all have to be, but I'm just, this is a basic piece of literacy that comes up a lot, okay? Now let's do one with a hippo. You want to learn about the hippo? Okay. What's that? They are dangerous, right? Because they're so fierce and strong. And they have giant teeth, and their bodies are really heavy, but they can actually move really fast. They're territorial. Yeah. Should we look up YouTube videos of people getting mauled by hippos? What's that? Well, I mean, yeah, they probably definitely sedate them. Then once they're in a cage, like, What's that?
Huh?
What's that? Hippopotamuses are vegetarians.
They are.
Yeah. No. You know what? They actually go on land at night and graze. They are in the water to regulate their body temperature and also to avoid predators during the day. What's that? They're mainly dangerous to humans if you walk into their. The reason why people say hippos are dangerous is because, like, actually, if you accidentally like walk into like hippo territory, they'll like attack you. But they are vegetarians. Yeah. I can't hear very well, but I like this conversation. Just, we should do the problem now. Okay, ready? All right. The blood circulation time of a mammal. This is very general. Are hippos mammals? Yes, they are. Directly proportional to the fourth root of its mass. Everybody translate that. What is that? The blood circulation time of a mammal is directly proportional to the fourth root of its mass. Hey! The hot chocolate's ready. What's that? What did I say? Hot cocoa?
Yeah, I know.
I said hot.
Am I gonna kill everything? What's going on?
Oh, yeah, you hit dispense.
like a
Oh, you have to hit unlock and then dispense.
Oh, okay.
Okay. So while you're getting your hot chocolate, did you write this? Did you write that T must equal K times M to the 1/4 power?
Yes.
What we have is a piece of information about a hippo that allows us to solve for the constant of proportionality. For the hippo, okay, hippo facts. And I'm not sure how true this is. 2,520 kilograms goes with, you press unlock and then dispense. Goes with 123 seconds. And I say goes with, really what I mean is like the mass of the thing means 123 seconds to circulate. So what this does is this tells us, this gives us the hippo proportionality constant. What can we do? We can solve for proportionality constant. Proportionality. It's not just the hippo one, it's just proportionality constant. Okay. And basically you're just plugging in the points. You substitute, right? So T equals some constant K times M to the 1/4. For the hippo, we just substitute things and then solve for K. Okay, which one goes where? Now here is something where oddly enough, the AI things are really bad at this kind of algebra. Like people, I haven't finished like assigning scores to the checkpoint 7 thing, but I was looking at the stuff people posted that was like, oh, I use this AI thing. And it was like, it starts off well, and then like, they just like mess up the algebra. So for some reason, the AI things that are available are not fully utilizing the computer-based algebra systems very well. So anyway, do not trust the algebra of AI things right now, just saying. Double check things. The setup often is good, like the AI will set up the equation you need to solve, and then, but when it goes through solving it, they mess it up a lot. I'm just saying. But for us, right, so because of this relationship, I can write down this number. And that is my value of k. I don't have to simplify it. But I can certainly get a decimal value, or I can just work with this ugly ass number. And it turns out you actually can simplify this, but I'm not going to get into that. Point is, this thing right here is about equal to some number. Okay? Well, what is it? It's 123 divided by 2520 raised to the 1/4 power. It's about 17.3602. Okay? So which one is the exact value? This is the important part. You need to know that this is the exact value. And what is this called? This is the approximate value. Approximate value of k. Okay? So what I have now is my relationship. I have a formula now based on this data. The formula here is y is equal to k is this, 123 divided by 2520 to the 1/4 power times the mass raised to the 1/4 power. Okay, this is approximately equal to 17.3602 times mass to the 1/4 power. And mass to the 1/4 power. Okay, same thing. This is a power function. Is this an exponential function? It's not exponential. Exponential functions have variables in the exponents. These are constants in the exponents. You gotta know the difference. Okay, so now answer the question. Oh, and I used y. I should have used t, right? T. My y is not y, it was t. And then I'm going to say find t for a line with mass. What do we say? Mass 180 kilograms. Dang. Okay, everyone go. Do it. Shout out the answer when you get it. Yes.
I have 63-ish.
Did anyone else get 63-ish? Morning.
33.
You got 33.58. Oh, a disagreement. Well, I'm not saying you're wrong. Helen might be wrong. I don't even know. What'd you get, Sophia? Wait, did you say the same thing? Did you say 63 or 33, Mon? Okay. That is different. What's that? Well, if math is a democracy, then 63.58 would win, right? But math is actually not a democracy. You could all be mostly be wrong, and Monica could be the one right. Monica is right. No, I'm just kidding. Let's check the reasoning, right? What do? T is going to be this big number, 1, 2, 3 over 2, 5, 2, 0 to the 1/4 power. And I actually think the 63 people are right, just so you know. But we're just going to substitute this. But we have to do the 4th root first and then multiply by k. This is just k, all right? And I am writing the whole thing out just to show you that you don't have to be afraid of a big number. It's just there. What do? You have to know what to do with it. We're going to take the 4th root of 180, and then we're going to multiply by the k. Ready? And to tell, oh look, haha, Desmos is so convenient. You know why? Because I can just call this thing k and then use it down here as k. I'm going to do k times 180 raised to the 1/4 power, and I get 63.587697. So I'm just going to say it's about 63.6. Okay? And that should be in units of seconds, right? The lion's blood circulates entirely throughout its body every 63.6 seconds. All right. Now, that's all I really wanted to do with this, was to make sure that you saw the this language of inverse and directly proportional. Okay. Now, we're not gonna be finding power functions through points, but if I were going to, it would be a very similar process to this one. This problem, but let's just do one last example, which is this one, which is also a physics example, which is actually also true. It's also a true fact. The pressure P exerted on a sample of hydrogen gas is inversely proportional to the volume V. Okay, so everybody see this? Translate this into a formula. This is known as a inverse variation formula. So we have a P. We have a V. We actually did this one already. It's equal to that. If V equals 2 liters, then P is equal to 1.5 atmospheres. And you don't even have to know what those units mean to get your proportionality constant, right? So, what? So K is, well, I have 1.5 is what you get when you plug in 2 for P, and so what does K equal? Three. Okay, so our function is this. P is equal to 3 over V, okay? Now, these are this kind of thing makes, I like these kinds of questions. This one isn't that. How much pressure does the sample of gas exert if the size of the container is cut in half? This is our little formula, our relationship. The question is, what if volume is cut in half? What happens to the pressure, okay? So what we're gonna do is I'm gonna say volume 1 is equal to 1/2 times some volume 0, okay? And what you do is you think about, suppose P0 is my 3 over volume 0, okay? What's my new P1? P1 is gonna be 3 divided by volume 1, and I can make a relationship. Okay, so now if I cut in half the volume, basically what you're doing is you're compressing it. You're basically taking something and squeezing it to half its volume. If it's gas, you can squeeze it. What happens though? The pressure goes up, right? If I have some bigger container and then I squish it down to a smaller container, the pressure is going to go up. This is going to tell us exactly how the pressure will go up if I go from a 2 liter to a 1 liter, for example. But in general, so my P1 is equal to 3 divided by, can I just replace this with my 1/2 V0? V0 is like the old volume, V1 is like the new volume. It's half the size of, right? So what happens if I divide by 1/2? What is 3 divided by 1/2, friends? It's just 6. So this thing is equal to 6 divided by V0. Which, isn't that the same thing as 2 times 3 divided by V0? And isn't that the same thing as P0? The pressure doubles. You get twice the pressure. Half the volume means twice the pressure. That's a direct result. That's a direct result of the inverse variation relationship. It means that, like, if I take something and make it smaller, but I keep the same amount of gas inside, the pressure goes up. Right? How would you write that what? So no, I can't actually hear you very well. Will you ask a little louder?
So like when we're doing when you're gonna explain it, I'm just asking, because like when we're transferring it to the formula, like it's gonna be, the pressure's gonna double.
Yeah.
So do we put it out?
2p0 is how I wrote it, right? Which is basically like, it basically means this is true in general. This one in the box, right? So for some volume of gas, the pressure it exerts is 3 divided by that volume. You get the pressure, okay? So if I make that denominator half the size, it makes the entire quantity twice as big. That's basically all it says. So if I shrink the volume, if I shrink this, cut this denominator in half, that makes the entire pressure double. So all I did here was symbolically show that that was true. I just showed where if, right? So if my V1 is equal to 1/2 V0, and I'm thinking of my original pressure, this is the original pressure, okay, given with the original volume, then here's my new pressure. The new pressure would be P1, and that's 3 divided by my new volume. How did my new volume relate to the old volume? It was half its size. And so, how does the new pressure relate to the old pressure? This one. This basically says, if I say, new pressure is 2 times the old pressure. Huh? I did 2 times 6. Okay. So here, this 6 is really 2 times 3 over V0, right? So all I did was factor out the 2. Huh? Yeah, because I had 1/2 in the denominator. Okay, so when I went from here, it was like, oh, P1 is equal to 6 divided by V0, right? 6 divided by V0, is it not equal to 2 times 3 divided by V0? Just think about this fact, isn't it true? Whoa. It's true. Basically, what happens when you divide something by 1/2? You multiply by 2. Let's try another one. Ready? A circle's area, does anybody know, varies directly or inversely? Not varies. A circle's area is directly proportional to the square of its radius. Did you know that? I bet you did. What's the formula for the area of a circle like that? The area is equal to a constant k times r squared. And we call this special proportionality constant, we know this one, it's the Greek letter pi. Hey! So here's my question for you. What happens to the area if we shrink the radius by 1/2? What happens to it if we double the radius? what happens? So if I start with something like pi times r squared, okay? I'm gonna say instead of just r, I'm gonna divide it by 2. 1/2 r squared. What happens to the overall area? Well, we know the area is gonna get smaller, right?
Yeah, but comes to the
Huh? Oh, the exponent just squares it.
yeah, the ones on the inside, but it's the
Sorry. Okay, so let me do it this way, okay? So we know that in general a is equal to pi times r squared, okay? Think of this as like the original circle. I'm gonna call this r0. Does that confuse you if I put a little 0 there? This just means like I'm talking about a specific circle. In fact, I'm gonna just draw r0 right here. Let that specific one be r0, okay? Now I'm gonna cut this thing in half. So now I'm gonna make my new radius, that one's gonna be r1, okay? Is that okay? How does the r1 relate? Okay, so this is my original one. Now I'm gonna call that a0, it's gonna be the original area, okay? New area, what happens to my new area? It's gonna be pi times, what am I doing? How did I get r1? I did r0 over 2 squared. I halved it, okay? Now, square everything. Pi times, isn't this r0 squared divided by 2 squared? Did you know that we can do that? Right? And so what happens? This is pi times r0 squared over 4, okay? Which means if I factor 1/4 out, then it's this. Now, how does my new area relate to my old one? And if there's a step, wait, do you follow these steps? Helen? Helen's looking at me or looking up here with skeptical looks. Which is good, you should be skeptical. But so what happened to the area? It got smaller by a factor of 1/4, aka we divided the area by 4. This is 1/4 of the original area. Okay. Direct variation by the square means that if I decrease something by half, then the whole thing gets decreased by 1/4. No, this is just a new example, okay, of variation. This is not an inverse. So this is direct variation. So if I'm directly varying, if I make the thing smaller, then everything gets small. Over here in inverse variation, I made the thing smaller and the pressure got bigger, right? So making one thing smaller makes the other one bigger. That's inverse variation. This one is direct variation, but it's direct variation by the square, which basically means like you should always buy the bigger pizza because, yeah, sorry, go ahead. Yes, you can. Of course. I would never say you couldn't. So what happens if we double the radius? Now I have like, here's r0, here's my r0, and I do another one. What happens to the new area? Right? This right here is like my a0 in here. What happens to my new area where there's like 2 area, right? What's the new one? What is my a1? It's gonna equal exactly like you're saying, you just factor it. 2 times r0 squared, right? Yeah, we get 4 times the area. Oh. So which pizza is a better price per square inch? The bigger one. Pretty much always. Pretty much always. So if I get a 10-inch pizza versus a 20-inch pizza, I'm getting 4 times more pizza. All right. Okay. All right. So that's all I really wanted to say about this. But I do want us to now go to the polynomial part. Okay. So is that okay? Actually, I need to take a brief break. I'll take a break. We don't do that enough. Take breaks. I'm gonna pause recording. Here's an example of a polynomial of degree 5. Here's an example of the power function that just is the lead term. If I zoom way out, these functions become nearly indistinguishable, and that tells us that in order to know what happens at the endpoints of a polynomial, all I have to do is look at the first or lead term. Okay, so I know that this function must go to infinity on one side and negative infinity on the other side. I know that just because it looks like a 5th degree power function from far away. That is what we're writing in here. Okay, so and we'll get quickly to the examples below. This is known as, okay, this is known as the global behavior. The global or long run behavior. Is determined by the lead term. Is determined. Wait, is that how you spell it? Determined. Determined by the lead term. And that's y equals a sub n times x to the n. It looks like a power function. That's why we talked about power functions, and now we're talking about polynomials, because from far away, any polynomial looks like a power function. That's it. Okay? Now, look at this last fact. Fact 3. When a polynomial touches but does not cross the x-axis, the factored form of the polynomial will have an even number of factors. Okay? Right? Great. What the hell does that mean? Here we go. Consider this polynomial. Okay? Fact 3 is very important, actually. And basically you have a polynomial, but I've written it in terms of all these factors. Right? This is factored form right here. Okay? What are the zeros of this? What are the zeros of my polynomial p of x? Where does this function go to 0? Do you remember how we look at that? What values of x would make it go to 0? Let's go from left to right. Do you agree with that? P of each of these things, I plug in x for each of those things, I get 0, right? Huh? Hmm? So look at the graph. Boom. Does the function hit 0 at each of these places?
Yeah.
Yeah. Okay. Fact 3 is kind of like a way of saying the exponent on that factor that makes the 0 determines what we call the local behavior. So like right here, doesn't it look like a line crossing through there? It looks like a first degree thing. And then right here, doesn't that look like a parabola? Right? And so notice that this x plus 2 has a second degree. And the other ones are first degree, so they look like a line, and then they look like a line, and then what's going to happen? Yeah, it's going to bounce off the x-axis. And then it bounces off the x-axis at 3 as well. Right? So what we can say is that the local behavior, we can call this local behavior, is determined by the zeros of a polynomial. Meaning, like, if I zoom in on a polynomial and I see what's happening at its zeros, we call that local behavior, like really zoomed in. Okay? Global behavior, now let me ask you this. What can you tell about the degree of this polynomial? What's the degree of this polynomial? Is it an odd degree or even degree? And how do you know?
Is it gonna be like all like because of that or that?
Uh-huh. On one side it's going up, the other side is going down, at negative infinity, it's odd. Because from far away it's going to look like this. This is the global behavior. See, all these humps and lumps are just local behavior. Zeros and turnarounds and all that stuff. Yeah.
Why is it odd?
Because odd power functions go infinity in one direction and negative infinity in the other. Even ones go to positive infinity. They go to the same direction. Okay? So we can also tell what's the degree. Like, I can actually tell exactly what the degree actually is. So notice that there's nothing multiplying the x's. If I was to FOIL all this stuff out, it's just x times x times x times x times x times x. This would literally be x, there's an x squared times an x squared times an x times an x times another x squared times another x. So if you FOILed this thing out, if you expanded it, it would look like x to the 1 plus 1, 2, 3, 4, 5, 6, 7, 8, 9. X to the 9th power. Plus a bunch of other stuff. Right? This function actually is x to the 9th power plus da 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 da. The degree of this polynomial is 9. And I can tell by thinking about what would happen if I tried to multiply all this stuff out. Do you believe me? So it is an odd degree. Also, let me ask you about because as x goes to plus infinity, y goes to plus infinity, and as x goes to negative infinity, y goes to negative infinity. So it has to be odd degree. Okay? Now what about turnarounds? How many turnarounds does it have? Turnaround points. This one is a little less Because a function of high degree doesn't have to have that many, doesn't have to have n minus 1 turnaround points, it just can't have more than that. But how many turnaround points are there? There's actually 8. So this just tells us the degree is at least 9, okay? Because if it was less, the degree was less than 9, it's not possible for it to have 8 turnaround points. But I can also tell in this example that the degree is 9, okay? So it makes sense that it has 8, okay? All right, so these are just facts. Now one more definition, and then we're going to do our examples. Okay, ready? Let P of x equal, okay, a polynomial. And we're saying that this lead coefficient is not 0. So we're just saying that whatever a to the n is, it's not 0. If it was 0, then it really wouldn't be nth degree. Then the number an is called the leading coefficient of P. Basically, the leading coefficient is the number in front. That's the leading coefficient. It's really not that complicated. Okay, so ready? We're going to find leading coefficient and constant coefficient. Constant coefficient is just the thing you add that doesn't have any variable multipliers, right? Okay, so what's the lead coefficient, friends? Mm-hmm. Mm-hmm. It's fine. That's the lead coefficient. A0 is -1. Negative. Right? So you think of it as plus -1. That's the same thing as -1. Okay? And what do we think about the end behavior?
Wait, why is it -1?
Because if
Oh, I'm sorry, it confused me.
that's A0 is the constant one. Yeah. A0 is, yes, A0 can also be thought of the polynomial function evaluated at 0, which is -1. Same thing in this case. Like if I plug in 0, that's 0, 0, 0, -1 is what's left, okay? But it's just when it's expanded like that, you just look all the way at the end, and it's the one with constant. There's no x. Okay. What else are we gonna? Okay, so what do we know about the global behavior?
Unknown color.
Who is this? Scam likely? No. I don't know who that is. Working? Get out of my face. Now, what's the global look of a 4th degree thing? The global look is going to look like y equals 3 times x to the 4th. And so it's going to look like this from far away. Isn't it? Even power function. It's not flipped over, right? Okay, so as x goes to plus, since it's even, we can just put it all in one statement. It doesn't matter if I'm going to positive or negative infinity, my function p of x goes to only plus infinity. It's going to go to plus infinity on both sides. True story. Do you believe me? I know you believe me, but I'm going to try to convince you anyway by plugging it into Desmond, shouldn't I? 3x to the 4th. What were the other numbers? I don't remember. Something, something, something minus 1. Doesn't really matter what the other ones are, except I should not have there. What was it?
5x to the power 2.
And that was it?
Plus 6x.
Oh,
Minus 1.
okay. Yeah. Look, great. So where does it go? Aha, global behavior. Looks like indistinguishable from y equals x to the fourth power. Does it go to infinity in both directions? Yes. Does this seem like there's some really easy patterns in these problems? Yes, exactly. That's why we like polynomials. You can master them. But it turns out there are deep mysteries which branches of mathematics tackle. But for us, we need to know the core behavior of them just by looking at their equations. Now, what if I foiled this up? Just for the sake of, making it look more familiar. Isn't this x cubed minus 3x squared? For number 2?
Yes.
Is that the same? It's equivalent. That's an identity. X squared multiplied by x minus 3 is x cubed minus 3x squared. When I say identity, I just mean this is an equation that's always true. Okay? Now, so what's the lead term? What's n? N is equal to 3. So what's my lead coefficient? A sub 3 is equal to, what's the lead coefficient here, friends?
3x. It's just 1.
It is just 1. The lead coefficient is 1. Who said that? One times x cubo. What about a0? Is there a constant?
No.
Nope, 0. What about the end behavior? What about the global look? One of those what? Tomato things? No.
No one was negative.
Yes, exactly. As x goes to plus or minus infinity, q of x goes to plus or minus infinity, we can say. And what we mean is like it goes to plus infinity on one side, minus infinity on the other. Okay, hopefully that's not too confusing and you understand what I mean. What about r of x? Okay, r of x is a little trickier. Okay, the lead term, if I multiply all this out, I know it's going to be 2x squared times minus x is the lead term. Plus a bunch of other stuff. Plus, and then I know the constant term is going to be negative 3 squared times 4. And I know some of you are like, what the fuck are you talking about? Well, do the algebra. 2x por 2x igual 4x cuadrada. Menos 3 por 2x por 2 igual menos 12x. Menos 3 por menos 3 igual 9 positivo. Now I do this whole thing by 4 times minus x. Huh? Okay, this is gonna equal, multiply everything by 4, 16x squared minus 48x plus 36, and then I'm gonna multiply everything by minus x. Then it's gonna be minus 4x cubed plus 12x squared. Oh. This is dumb. I mean, not dumb, it's just, I'm sorry. Minus x times minus x times plus 9 is going to be minus 9x. And if I organize all these things together, what? I get negative 4x cubed. X squared plus 28x squared. You guys aren't really following this algebra right now? You're like, not like, oh, wait a second. Yeah. Okay, 12x, 16x, 12x squared, 16x, minus 48, minus 9, that's gonna be 9, minus 57x plus 36. Yeah, I was saying do it with me, but it's all right. We don't have that much time. The point is that if I multiply all this stuff out, I get this function, okay? This is equivalent to this function. But I was trying to show you, or at least I was trying to mention, that I could tell the lead term and the constant term just by looking at this, which was the biggest degree is going to be all of these things multiplied together by all of those things, right? How many 2x's are there? There's 2 of them. 2x squared times how many minus x's are there? There's 1. So this literally is minus 4x cubed was the lead term. This is going to be how many constants are there? There's 2 constants, or there's a constant that gets squared there, negative 3 squared, and then there's 1 constant here. So negative 3 times negative 3 times 4 is going to give me my constant term, and that is 9 times 4 is 36. And all the rest of it is stuff I didn't really care about. My point was like I went through all this because I didn't actually need to. These middle ones don't actually play as an important role as the first one and the last one. So to answer these questions, all I needed was the first one and the last one. So what's the degree of this polynomial? Yeah, n equals 3. What's my a sub 3? What's the coefficient? What's my lead coefficient? Is it 4 or negative 4? And what's my a sub 0? Okay, now let's be more careful here. What's the global look? It looks like y equals negative 4x cubed, which means it's like a vertical flip. This means it's an upside down one. Oh. So as x goes to positive infinity, what does my function r of x do? R of x goes to negative infinity. And as x goes to negative infinity, what does r of x do? R of x goes to plus infinity, okay? And we can tell that just by looking at the lead term. By the degree and the lead coefficient. Excuse me. It spilled all over my tongue. I got a drinking problem. All right, well, now I don't have that much time for the things. Look at this. How many turnarounds? 1 turnaround. How many zeros? 2 zeros. Suppose I wanted to find an equation for this.
Just 1 turnaround?
There's 1 turnaround, so it's degree at least degree 2. Also, the zeros look like linear first power zeros. So I know that this function is something like some constant a times x plus 1 to the first power times x minus 3 to the first power, right? And I need negative 3 to be the y-intercept, so a0 is going to be a times 0 plus 1 times 0 minus 3 is going to equal 0 plus 1, yeah, a times negative 3 And I know a0 has to also be the y-intercept, so I know that this has to equal -3. Sorry, that was confusing. Let me do this. Y-intercept is going to must equal -3, which is going to equal whatever my coefficient is times all of this, okay? So what do I have? So a has to equal -3, and my final function is, no, a does not equal -3. -3 times a has to equal -3, so a equals 1. Jeez. So y is equal to x plus 1 times x minus 3. So this is us bringing together our polynomial knowledge to find equations for polynomials from the graphs. Yes? Go ahead. Wait. Go ahead. You talk louder. Yes, quadratics are in the family of polynomials. Yeah. Everything we're saying about polynomials applies to both quadratics and linear functions. They're all in the family. Polynomials is now just a bigger family than the quadratics. Okay, what degree is this? What degree do you think it is? There are 2 turnaround points, and there are 3 zero crossings. Must be at least degree 3. So what do we know? We know that this thing is going to equal y, and because I know the zeros, I can say, oh, this is x plus 3 times x plus 2. And see how, like, when you zoom in, they're crossing through? They cross through. So I can just consider those first power. And then this one's like x minus 2 to the first power because they're crossing through. Then I need -24 to be what I get when I plug in 0. No, I'm rushing because 3 times 2 times -2. Oh, 2 times 2 is 4 times 3 is, this is -12. So -24 is equal to a times -12. Therefore, a is going to equal -24 divided by -12, which equals 2. So a equals 2. So y is equal to 2 times x plus 3 times x plus 2 times x minus 2. We can do this all day. Something like this. Hey, what about this one? Let's do this one.
So would that be 4th?
What are the zeros? Yes, it's like at least 4th degree, because notice I have 1, 2, 3 turnarounds. So there's at least 4th degree. Huh? And there's going to be some negative coefficient. We're going to have to figure out what it is. But first, what can I write down about this quartic function? It's going to be some constant multiplied by, in factored form, this. Now, is that a quartic function? What do I have to do? I have only 3 x's here. If I multiply them all out, I get x cubed. Yeah.
Are we going to find that? Or, oh wait, no, because it's
What's happening at that -1 spot?
first always.
It's a turnaround point and a 0. Which means it's bouncing off the x-axis, remember?
Okay. So you can see it's next where it's bouncing off.
That means that it's a squared factor. It looks like a parabola. So this thing has to be so it's bouncing off. Okay. Now we need when x equals 2, we need y equal to 1. So we plug in 1 is equal to a times 2 plus 1 squared times 2 minus 1 times 2 minus 3. And I get a 1 must equal a times 3 squared, which is 9, times 2 minus 1 is 1, times 2 minus 3 is negative 1. So I get 1 is equal to negative 9 times a. And therefore, what is a? A must equal negative 1/9. Therefore, notice that the global behavior now is therefore negative 1/9 times x to the 4th power. So my formula here is, oops. Okay, everyone try to write down the formula. Y equals negative 1/9 times x plus 1 squared times x minus 1 times x minus 3. That's it. So what's the lead term? Lead term is negative 1/9 x to the 4th plus plus the constant term is going to be 1 times negative 1 times negative 3. It's going to be negative 3 times negative 1 is positive 1 times positive 1. It's going to be negative 1/3.
Are we gonna get more practice with this?
Yeah, do number 5. But also, let's look at what the homework is real quick. This is basically what I have for 5.2. But there's other aspects of 5.2. I assigned a read and preview for 5.2. Now that we went through it, should be hopefully reinforcing for you. And on Wednesday, we're going to go 5.2, 5.3. So we'll practice more of this on Wednesday. And you can look ahead. What's that? Oh.
He was doing it on his class. And then I tried one and I didn't like it, but
What is it like?
Okay, friends, if you look at the web work, I don't think it's that. So we should be able to do most of these polynomial exercises, okay? These ones are like, can you tell a polynomial from a non-polynomial? If something is not a polynomial, we do not say that it has a degree. So I would say jump to these exercises and see what you can do. Because I actually think that you could do a lot of now. Oh, some of these estimating the zeros is you literally just graph it in Desmos and click on where it crosses 0. Okay, that's it. That's how you estimate the zeros. You're supposed to, use technology. Now this one they want exact answers. Okay. This one they want exact answers, so you'll have to know how to solve this thing. Basically, you'll set that factor equal to 0, and you have to take the 5th root of something. Anyway, we can do more with that stuff, but go ahead and you can probably pretty much finish this homework. Because look, it's just giving you this and saying as x goes to infinity, which way does it go? And hopefully what we talked about today, you can be like, okay, this is 4x squared, that means it's second degree times a negative first degree thing, that means it's gonna be a negative times a third degree thing, so it's looking like as x goes to infinity, f of x is gonna go to negative infinity. The kind of reasoning we were just doing, you can do it here, okay?
Thank you.
That's it, go off into the wild. Enjoy your time. Make time for math, make time for yourself. Bye.